In this video, I'm going to show you how to evaluate these 6 integrals that came out in MIT Integration Bee 2019. Let's get started. First integral, so we have here integral of cosine x cosine of sine x times cosine of sine x dx. We can easily evaluate this by u substitution. So we let this expression here to be our u, and if this is our u, du will be equal to, so derivative of sine of a function. It's like sine of u is equal to cosine of u. Your u in this case is like sine x, if you're thinking of it as derivative of sine u. So that is derivative of sine u is cosine u times the derivative of u with respect to x, but this is your u, and the derivative of this with respect to x is equal to cosine x. So this is times cosine x, and then dx, which is actually the remaining factor in your integrand. Okay, so therefore we can write this integral as simply equal to cosine u, integral of cosine u, and then du, which is equal to sine u plus arbitrary constant c. And then we put back the u in terms of x. This is equal to sine of u is equal to sine of sine x, and then plus arbitrary constant c. Now let's move to the next integral. So for this second problem here, we have integral from 0 to infinity e raised to the negative of 2019 over 4t squared all over t squared dt. This looks like a Gaussian integral, if we're going to recall what a Gaussian integral is. Okay, we have so Gaussian integral. It is in the form. Okay, so we have integral from negative infinity to infinity of e raised to x squared dx. This is a famous integral, and the value of this is square root of pi. Of course, the integrand here is an even function, so we can also write this down as, let's say, integral from 0 to infinity of e raised to negative x squared dx equal to square root of pi all over 2. Why does this second problem look like this Gaussian integral? Because we can write it down as integral of, let's say, 0 to infinity of e raised to, let's say, the negative of, in this case, square root of 2019 all over 2t, and then quantity squared times 1 over t squared dt. And as you can see, if we let u to be equal to this expression inside this parenthesis, so you have here 2019 all over 2t, then our du is equal to negative square root of, you have here square root of 2019 over, so you have there 2t squared, okay, and then dt. So that is the du in this case. So therefore, this implies that negative 2 over square root of 2019 is equal to, so this is times du, is equal to 1 over t squared dt. So therefore, we can write down our integral as integral of e raised to negative u squared, and then times 1 over t squared dt is equal to negative 2 over square root of 2019 and then du. And what are the limits of integration? So if we look at this 0 here, so as we approach 0 from the right, so as t approaches 0 from the right, so this u here approaches infinity. So therefore we have here infinity, and as t approaches infinity, then this u here goes to 0. So the upper limit of integration in this case is equal to 0. And if we're going to interchange these limits of integration, then we have to multiply the integrand by -1. So by interchanging these limits of integration, we have here 0 to infinity of, so we can pull out the constant in this case. So you have here 2 over square root of 2019 integral from 0 to infinity of e raised to negative u squared du. And since this is a famous integral, and the value of this is just equal to square root of pi over 2, so therefore the value of our integral is 2 over square root of 2019 times square root of pi over 2, which is the same thing as square root of pi all over 2019. Next problem. So let's consider this integral of sine square root of x dx. So let's try again u substitution in this case. If we let this square root of x to be our u, then our du is 1 over 2 square root of x dx. So you just apply ordinary power rule. And this will give us 2 square root of x du equal to dx. But square root of x is u. So therefore, we can write this down as 2u du is equal to dx. So our integral in this case can be written in terms of u du as integral of, you have here sine u, and then times 2u du. So let me write this down as an integral of 2u sine u du. So just by looking at the form of this integral, this is telling us that we have to do integration by parts. So by applying integration by parts, so if we let this to be our, let's say, mu, because we already used u here, so let us consider that as our mu, and then this one here as our dv. So it's like integral of mu dv. So this is equal to, by integration by parts, we have here mu v. So mu is equal to 2u, and then times v is the integral of dv. So you have your integral of sine u du is equal to negative cosine u. And then minus integral of v d mu in this case. And your v is negative cosine of u, and then your d mu is actually equal to 2 du. So again, this is just integration by parts. So integral of mu dv is equal to mu and then times v minus integral of v, and then this is your d mu. So therefore we have here negative 2u cosine of u, and then plus, in this case we have plus 2 times integral of cosine u du, so that is plus 2 sine of u plus c. And then again, putting back the u in terms of x, we'll get here negative 2 square root of x cosine of square root of x plus 2 sine of square root of x plus c. Now, moving to problem 10. So we have here integral from 0 to 1 of square root of x all over 1 plus x dx. If we use again u substitution in this case, so probably you could try the denominator to be your u, but if this is the u, it won't make this integral less complicated. Now, another choice for u in this case, keep in mind that if we go back to our integral formulas, we have a formula wherein the denominator is in the form 1 plus u squared. So it's possible to handle such an integral because we have an integral, let's say integral formula, integral of 1 over 1 plus u squared du is equal to tangent inverse u. So a possible u in this case is, if we're thinking of using that formula, integral of 1 over 1 plus u squared, so this is like in the form u squared, then a possible u is also a square root of x. So we can try that as our u. Okay, so u here is equal to square root of x. Then again, our du, same as in the previous problem, our du is 1 over 2 square root of x dx. And then again, here you'll get 2 square root of x dx equal to 2 square root of x du is equal to dx. So therefore, this is 2u du is equal to dx. And we can now write our integral as integral of, you have here u all over 1 plus u squared. And then our dx is 2u times du. And what are the limits of integration here? So when x is equal to 0, u is square root of 0. So that is also equal to 0. When x is equal to 1, again, square root of 1, u is equal to 1. So same limits of integration, integral from 0 to 1. And we'll get here integral from 0 to 1, 2u squared all over 1 plus u squared du. Now, this 2u squared over 1 plus u squared can be written as, in this case, we can write it as 2 times u squared plus 1, and then minus 2 all over 1 plus u squared du. Okay? And therefore, we can write it down as integral from 0 to 1 of 2 minus 2 over 1 plus u squared du. You'll get the same thing when you do long division for this expression. You can do long division here because the numerator, the degree of the numerator is equal to the degree of the denominator. This is an improper fraction. So you can do a long division. And after doing long division, you'll get this one. But of course, you can also do something like this, algebraic manipulation here. And from this, we can easily integrate, okay, this integral. So we have here integral of 2. So you have here antiderivative of 2. So that is 2u minus 2 times tangent inverse of u, evaluated from 0 to 1. So therefore, this is equal to 2 times 1. So that is 2 minus 2 times tangent inverse of 1. And tangent inverse of 1 is just pi over 4. And then minus, you have here 0 minus 2 times tangent inverse of 0, which is equal to 0. So this is just minus 0. So therefore, the final answer is 2 minus pi over 2. Now let's move to the next integral. So we have here integral from 0 to 2 pi of cosine x times cosine 2x times cosine 3x dx. To evaluate this integral, all we need to do is to use the product to sum identity for product of two cosines. Okay, so if we're going to recall that product to sum identity, we have here cosine of A times cosine of B. We can write this down as 1/2 of, you have here cosine of A plus B, and then plus, you have here cosine of A minus B. Okay? So using this identity, we can write this product here as 1/2 of, you have here cosine of, you have the sum, so 2x plus 3x, so that is equal to 5x, and then plus cosine of the difference, so that is equal to 2x minus 3x, that is negative x. But since cosine is an even function, we can make this negative as positive. So this expression here, cosine of A minus B, is the same thing as cosine of B minus A, because cosine is an even function. So therefore, we can now write our integral as integral from 0 to 2 pi of 1/2 of cosine of x cosine 5x, and then plus cosine x times cosine x, so that is cosine squared x, and then dx. And again, we use this identity, okay, for this first term here. And we can write that expression. So we have here integral from 0 to 2 pi of 1/2 of the cosine of the sum. So you have here cosine of 6x, and then plus cosine of the difference. So you have here x minus 5x or 5x minus x. So that is cosine of 4x. And then plus, now for this one here, we use half angle identity, okay, for cosine, and that is just equal to 1/2 plus 1/2 cosine 2x. And then this is times dx. So let us simplify a little bit the integrand here. So we can write the integrand as 1/4. So let's write down the constant first, and then you have here plus 1/4 cosine 6x, and then plus 1/4 cosine 4x, and then plus 1/4 cosine 2x dx. And we can easily find antiderivative of this integrand. So we have here 1/4 x plus you have here 1 over 4 times 1 over 6, so that is 1 over 24 sine of 6x, and then plus 1 over 16 sine of 4x, and then plus 1 over 8 sine of 2x, evaluated from 0 to 2 pi. So when x is equal to 2 pi, we'll have here 1/4 times 2 pi, so that is pi over 2. And then sine of an integer multiple of pi is just equal to 0. So this go 0, this is 0, this is 0. So this is just plus 0. And then minus, when x is equal to 0, all of these terms are equal to 0. So this is just 0. So therefore, our final answer is pi over 2. Now, let's look at this last problem here. So limit as n goes to infinity of the integral from negative infinity to infinity of e raised to x raised to 2n dx. So here, if we look at this integrand, it's an even function. So we may write it down as limit as n goes to infinity of, you have here 2 times integral from 0 to infinity of e raised to negative x raised to 2n dx. Now, if you look at this integrand again, for, let's say, for x between 0 and 1, the limit of this one is equal to 1, because this will approach 0 if x is between 0 and 1. So this will go to e raised to 0, so that is just equal to 1. But when x is greater than 1, so this will go to infinity as n goes to infinity. So therefore, this will go to what? E raised to negative infinity. This will go to 0. Okay, so we have like two functions that is approached by this sequence of functions as n goes to infinity. It depends on the value of x, whether x is between 0 and 1 or greater than 1. So in this case, it's important to just divide this into two integrals. So we can write this down as limit as n goes to infinity of 2 times, let's say we have here integral from in this case, let me write it down as, for example, 0 to 1, okay? 0 to 1 of e raised to negative x raised to 2n, okay? dx, and then plus, let's exclude the 1, okay? So this is just 1 to infinity of e raised to negative x to the 2n dx, all right? Because we know that this integrand here, okay, will just go to 0 when x is greater than 1, and then this integrand here will go to 1 when x is greater than or equal to 0, less than 1. So the values of this, even if we excluded the 1 in this case, they still have the same value, okay? So in this case, you may remove like finite numbers if you want in the interval 0 to infinity, but the values of the integral are still the same. And now, our goal is to, for example, interchange this integral here and this limit. And we can do that actually if the integrand is uniformly continuous, okay, here. Or we may also use a famous theorem. We call it dominated convergence theorem. And I'm planning to use that to find this integral. So we can use the dominated convergence theorem if we can show that the integrand in this case, it's like your f sub n of x, is bounded by an integrable function, okay, in your interval, okay. So, but if we look at this one here, okay, so this absolute value of e raised to x raised to 2n is equal to 1 over e raised to x raised to 2n. And actually, this is less than or equal to 1 for x greater than or equal to 0, less than 1. And keep in mind that this 1 here is integrable on 0 to 1. And therefore, we can use the dominated convergence theorem, and we can interchange the integral and the limit in that case. So for the second integral, we also have absolute value of e raised to x raised to 2n. Again, this is equal to absolute value of 1 over e raised to x raised to 2n. And this is less than or equal to 1 over e raised to x. And it is easy to show that this one here is integrable again on the interval 1 to infinity. So integral of e raised to negative x is just e raised to negative of e raised to negative x, and you evaluate that from 1 to infinity, you'll get a finite value. So that is integrable. So because this f sub n of x here, the integrand, is bounded by an integrable function in the given integral, okay, then we can use the dominated convergence theorem, and we can interchange the limit and the integral. So therefore, we can now write it down as 2 times integral from 0 to 1 of the limit of e raised to negative x to the 2n as n goes to infinity dx, and then plus again to integral of, again, in this case, we have 1 to infinity of the limit of e raised to x raised to 2n dx. Okay, but this is equal to what? So 2 times integral from 0 to 1 of, this is, the limit is equal to 1 in this case. Okay, so that is 1 dx. So that is for any x in this interval. The limit of this one is equal to 1. And the limit of this when x is greater than 1 is equal to 0. So this is as n goes to infinity. So this is just 2 integral from 1 to infinity of 0 dx. So this second integral is just equal to 0. Therefore, this is just equal to 2 times 1. Okay, 2 times 1, and then you have here plus 0, which is equal to 2.